Another day, another case. First it was negative numbers. People said they didn't exist. Then irrational numbers. Too crazy to be real. But this is the strangest case yet.
Boss, we've got reports of numbers that vanish when squared. Witnesses say they're negative.
Negative squares? That's impossible. Every number squared is positive unless...
Could these numbers be imaginary?
Where are they? Where could they be?
Imaginary numbers are based on root -1, which we call I. They help us solve equations real numbers can't. Imaginary numbers have a real part and an imaginary part, which they are used to be graphed on the complex plane. Complex numbers are numbers of the form z equals a plus ib, where a and b belong to real numbers. A is called the real part of z, and we write rez equals a, and b is called the imaginary part of z, and we write imz equals b. Complex numbers can be displayed in three different forms: the Cartesian form, polar form, or Euler's form. When a complex number is graphed on the Cartesian plane, the distance from that point to the origin is called its modulus, or absolute value. To find the modulus of a complex number, we must use the equation. Take the complex number z equals a plus bi. When that complex number is graphed on the plane, the distance from that point to the origin is called its modulus, or the length of the vector ab is called its modulus. To find the modulus of a complex number, we must use the equation z equals root a squared plus b squared. And this is derived from Pythagoras' formula, as you can see that any point forms a right angle triangle with the origin, which allows for the formula a squared plus b squared equals c squared to be applied to find the modulus. The argument of a complex number is the angle theta, where negative pi is less than theta is less than equal to pi, is measured anti-clockwise between the positive and real axis and the point. To find the argument, we apply the formula arctan b over a. So the polar form of a complex number is based on the modulus and argument of z, in which z equals a plus bi. So on the unit circle, with the x-axis as real numbers and the y-axis as imaginary numbers, the radius of the circle is also equal to the modulus, z, and at point P, a complex number, the coordinates are r cosine theta and r sine theta. And we define cis theta as cosine theta plus I sine theta. And therefore, a complex number z has polar form z equals modulus cis theta. So the modulus argument form or polar form of a complex number is simply the modulus of the number multiplied by cosine of the argument plus sine of the argument multiplied by I. So let us demonstrate this with an example. Take the complex number z equals -1 plus I. To convert this from Cartesian form into polar form, we must find the modulus, in which we use root -1 squared plus 1 squared equals root 1 plus 1 equals root 2. To find the argument, let's take the arctan of -1 over 1. However, since z lies in the second quadrant, we add pi radians to the result, which gives 3 pi over 4. Thus, this means that our number z equals -1 plus I is equal to root 2 cis 3 pi over 4 in polar form. We can also multiply and divide numbers in polar form. Take two numbers, cis theta and cis 5, that are multiplied against each other. Through expanding the multiple, we can use trigonometric identities, specifically the compound angle formulas, to derive that it is equal to cis theta plus 5. Property 2 is for cis theta divided by cis 5, which gives cis theta minus 5. This can be derived in a similar manner through trigonometric identities. Lastly, cis theta plus 2k pi, where k is an integer, is equal to cis theta. And those are the properties of polar form complex numbers.
I guess we'll never really know where they are.
At least we know they exist.